In this video, we're going to look at how to turn the bad leaving group that's on an alcohol, the OH hydroxyl group. We're going to look at how to turn that into a good leaving group. Let's jump right in. So alcohols have this hydroxyl group, which is a pretty bad leaving group. So if I wanted to do some kind of SN2 backside attack, that reaction does not work because this is a bad leaving group. We need to turn it into a better leaving group. There's a couple of ways of doing that. One way, we can take an alcohol, react it with an acid like HBr. So if there's an acid in there, a source of H+, where's the most negative spot on this molecule? Of course, it's these negative electrons, these juicy negative electrons. So they would attack the H+. Look at this good leaving group on there, this bromide which could leave. So this alcohol, now that lone pair is stuck on this H+, so this has a positive charge, plus we have Br- that left. Now this is a really good leaving group. If that leaving group leaves, we get a positive charge on the R group, and look what we made. We made a water molecule which is super stable. This is a great leaving group. It wants to be by itself. It wants to leave. It's super happy being by itself. So water is a great leaving group. And just to complete this reaction, since we have Br- in there and this positive charge, you can determine that that Br- would attack that R+, and we could end up with that OH group being replaced with the bromine. So let's take this alcohol and react it with another acid. But instead of HBr, we're going to use sulfuric acid. This is called a dehydrating acid. Because it loses water for us off of this molecule. And what's going to happen is we're going to lose H2O, and we're going to end up with this alkene. Let's look at the mechanism, how we get from here to here. If we have sulfuric acid, that lone pair can grab the H+. We have this great water leaving group. It can leave. To make this carbocation. And our sulfuric acid has some water in it. And that water can come and grab this H+, leave these electrons in to make my double bond, my alkene. So that's one way of turning an alcohol into a good leaving group to help water leave to make a double bond when I'm done. You can use sulfuric acid for that. Sometimes you see phosphoric acid being used for that. Both of those are dehydrating acids. Now some students get into the habit of always trying to use an acid to make this a good leaving group by turning it into water. But it's not always a good idea to do it that way. For instance, if I throw some acid in there, and make this a good water leaving group, and then I decide to throw something negative in there that's a good aggressive attacking nucleophile because I wanted to do this SN2 reaction, The problem would be this nucleophile would not do this backside attack. Instead, the nucleophile would just go grab this H+. So you're not allowed to throw something negative in there with something positive like this, because these two things get together and it doesn't do the reaction I want. Instead, what's better to do is take your alcohol, turn it into a good leaving group first. Maybe that could be like a bromide or a chloride or an iodide, something that you've seen in the past. And then you can throw in your nucleophile. And it can do your SN2 reaction. So let's learn how to turn OH into a good leaving group like one of these. There's one more I'm going to throw in there. We can also turn it into a tosylate. And we'll explain what that is in just a moment. So it depends on what kind of alcohol you're dealing with, what reagents you use to turn it into these different compounds. So here's a chart that you'll just need to learn. I made this little chart. You can pause it on this, maybe print it off. But these are the reagents I would memorize on how to turn alcohols into different good leaving groups. So in this chart, I have this alcohol. And if I want to turn the OH into an iodide, a bromide, a chloride, or a tosylate, these are the reagents I would use. Now the methyl alcohols, or primary alcohols with one carbon attached to the alcohol group, or secondary alcohols with two carbons attached to the alcohol carbon, they use these reagents. So if I want to turn the OH into an iodide, I use phosphorus and iodine. If you want to turn the OH into a bromide, you use phosphorus tribromide, PBr3. If you want to turn one of these OHs into a chloride, you use thionyl chloride, SOCl2. So phosphorus and iodine, phosphorus tribromide, thionyl chloride. And if you want to turn it into an OTS, which we'll show you in a moment, another good leaving group, ROTS, use tosyl chloride and pyridine. So pyridine is a good base. It looks like kind of a benzene with the nitrogen replacing one of the carbons. And it's a good base. So what I want you to notice is to make this you're going to pull off this hydrogen. It's going to react with this chlorine and HCl falls off. The base pyridine soaks it up and you end up with this oxygen bonded to the tosylate group to make a tosylate, ROTS. If you have a tertiary alcohol with 3 carbons attached to the carbon of the alcohol, if you want to turn the OH into an iodine, you use the acid HI. If you want to turn it into a bromide, HBr. We saw that mechanism earlier in this video. Turn it into a chlorine, you want to use HCl. Sometimes they throw in zinc chloride, that's called the Lucas reagent. And to turn it into a tosylate, it's the same reaction, tosyl chloride with pyridine. So these reagents you just need to memorize because you'll want to know how to turn an alcohol into a good leaving group. Let's take a closer look at this tosylate group. If I turn my alcohol into a tosylate, I could do an SN2 style reaction, a backside attack of the nucleophile, OTS leaves as a negative tosylate. Now this negative tosylate, let me draw what it actually looks like. It's a negative oxygen, and the TS part, the tosyl part, is a sulfur with a couple double bond oxygens on it, a phenyl ring, and a methyl. This is a very stable, happy compound that leaves. Let's show why. Well, this negative oxygen, I could draw a resonance form where I push electrons down and up onto oxygen to make the negative charge on this oxygen. Another resonance form I could push in and down to this oxygen and make a negative on this oxygen. So that negative charge can be shared over 3 different negative oxygens. So when you spread it out over 3 atoms, That spreading out of the negative charge makes it very happy, and so it likes to leave that way. So that's a good leaving group. Let's take one more look at this type of reaction and see why I might want to turn an alcohol into a good leaving group. Let's say I have 2 alcohols available to me. But I want to make something that looks like this. This ether. So how can I combine these 2 things to make this compound? Well, this is a bad leaving group and that's a bad leaving group. What you might want to do is turn this into a good leaving group. So we have a chart you can look up and we've memorized, and we can turn this OH into, let's say we want to turn it into a bromine leaving group. So I would use PBr3. And then I can turn this into an alkoxide, which we've seen in an earlier video, using sodium metal. So this alkoxide and this good leaving group, I could have a backside attack reaction occur, and I can make my final product. So I could turn this into a good leaving group, then my reaction would proceed. Hey, think about subscribing to the channel. That way, whenever you get stuck in organic chemistry, you know where to come for some extra helpful hints.